The last application is part of the Exabiome project on exascale solutions for microbiome analysis. Exabiome is one of the applications funded by the U.S. Department of Energy's Exascale Computing Project, ECP. Exabiome involves multiple applications to analyze large microbial datasets, such as the terascale datasets shown in this image. Some of the scientific questions addressed by Exabiome tools include: what happens to the microbes in the environment after a wildfire? How do microbes affect disease and growth of various types of crops, including switchgrass? Or over a 17-year period, how do microbes change in a freshwater lake, shown here with a large algae bloom? We'll focus here on what is often the first phase of microbial analysis called metagenome assembly. This de novo assembly problem takes raw sequence data, which is made up of fragments called reads. These reads are short, typically 150 characters long, and often contain errors introduced by the sequencing process. The problem is to determine how each of these pieces fit together to form the complete genome of a species. It's called de novo assembly because for most microbial species, unlike the human genome, we don't have a reference genome. It's like putting together a puzzle without the picture on the box to show as a reference. Now, microbes don't live in isolation, but typically live in large, diverse communities, often with hundreds of other species. So the sequence data is fragments made up these hundreds of species, and the metagenome assembly problem is analogous to putting together hundreds of puzzles with the pieces all mixed together. The Exabiome metagenome assembler is called MetaHitmer. It is the first metagenome assembler designed for distributed memory HPC systems, and by analyzing these terabyte data sets all together in what's called co-assembly, rather than analyzing, say, a few gigabytes at a time in what would be called multi-assembly, we've demonstrated that you can get better quality results. We can find more species, including some of the rare ones, and produce more complex genomes. This has also been demonstrated by independent benchmarking teams in comparing other state-of-the-art assemblers. One of the early MetaHitmer papers was a finalist for Best Paper Award at SC18, and this year a paper on the GPU-optimized version of one of the pieces is a finalist as well. A high-level summary of the assembly process is shown here. There are 4 main steps performed multiple times. It takes the raw sequence reads as input, and recall that these may contain errors, but they should also contain multiple copies of any region of the genome, so we filter out the erroneous fragments. We do this by chopping them into fixed-length strings of some length k called k-mers. We then count the number of occurrences of each k-mer and throw out those that occur only once because they're probably errors. We then take those k-mers and treat them as a graph where each k-mer is connected to the one on the left and the one on the right that occurred before and after it in the input. The connected components on these graphs will form contiguous strings we call contigs. These contigs are still relatively short, and we'll use the string alignment to align the original input reads back to the contigs and use them to extend the contigs. Part of this step involves a local version of this entire assembly pipeline performed on a set of reads that map to the same contig in order to resolve the ambiguities. The last step, called scaffolding, is a kind of graph walk to connect the contigs together and resolve any branches. The first step is k-mer analysis. This picture shows an example of what the k-mers look like. These are formers, and notice that they overlap, so there's a k-mer starting at every character in the input. 4 is a ridiculously small number for k-mers, but is used here for illustration. In practice, you would be using something like 21 or 51 mers, and this will blow up your data set by almost a factor of k. You don't need to keep all of these resident in memory at one time, and we will instead put them in a histogram with just one instance of each unique k-mer and a count associated with each. Because there are a large number of erroneous k-mers that occur only once in the input data set, it's useful to use a Bloom filter to remove these before adding them to the hash table. A Bloom filter is a statistical data structure that very compactly represents the set of unique k-mers approximately and filters singletons with high probability. The original version of the k-mer analysis code was written in MPI using collective communication. This graph shows the speedup of that version as well as the UPC++ version, which is asynchronous communication with and without the Bloom filter. Comparing the top 2 lines, the MPI version and the UPC++ version, both with the Bloom filter, you can see that both versions scale well across the nodes, but the UPC++ code is about 5 times faster than the MPI one at scale. It also saves significant memory in our setting because while UPC++ and MPI can run in the same application, it required extra memory to keep both runtimes around. The Bloom filter is useful for saving memory, but it also is a distributed data structure and incurs roughly the same kind of communication overhead as the hash table. So while the Bloom filter is valuable for saving memory, it can also cost more than double the runtime for K-mer analysis. K-mer counting is a fairly irregular computation involving random access updates to a distributed data structure. But it turns out, and somewhat to my surprise, that it can perform well when optimized for GPUs. The first graph shows the time breakdown for a K-mer analysis code running on 64 nodes of a CPU-based system. The second graph shows the GPU-optimized version, also on 64 nodes. One of the early lessons from this work is that counting is not the only thing that the GPU should do. It also has to parse the input strings into K-mers. That reduces the CPU-GPU communication volume and gives the GPU more work to do. Note that the y-axis in the second graph is smaller by 2 orders of magnitude than on the first graph. That tiny red sliver of communication in the first graph becomes dominant after adding GPUs, with a resulting speedup of over 100x. The third graph then shows additional speedup from optimizing the communication, using some application-specific techniques. First, it uses a hashed function that's based on substrings of the K-mers, which has the effect of putting nearby K-mers on the same processor, which will also improve locality for later stages of the assembly. In this stage, it allows a pre-parsed version of the K-mers to be communicated, so before that factor of almost k expansion, saving significant communication volume. The next step in assembly is de Bruijn graph construction. In this step, each K-mer is viewed as a node in a graph, and another K-mer that overlaps in k-1 characters will be connected by an edge. The K-mers are processed in such a way that branches are omitted, so the connected components of this graph will all be simple chains. The K-mer graph is stored as a hash table that comes out of the K-mer analysis stage. In addition to the K-mers, which are stored as keys, the hash table stores the left and right extensions, the character before and after the K-mer in the original read. We view this hash table as a graph and compute connected component strings by walking through a graph starting from any location. At each step, you look up a K-mer, add, say, its right extension, drop the leftmost character, and that forms the next K-mer to look up in the hash table. This can be done in parallel starting at an arbitrary location within the graph, albeit with some careful synchronization to handle the case where 2 threads arrive at the same K-mer and their strings need to be merged. This computation is communication latency limited because most lookups, p-1 over p in general, will be remote, although a good hash function, as described earlier, will improve that somewhat. Even in UPC++ with its lightweight communication layer, there is still an advantage to sending larger messages. This graph shows the communication bandwidth observed by messages of a varying size. A typical K-mer may be stored in only 64 bytes, and each successive insert or lookup may go to a different remote processor, so sending them one at a time will be very slow. The UPC++ MetaHitmer code therefore uses an aggregated store functionality, which is implemented as its own distributed data structure. Dynamically, it accumulates K-mers to be inserted into a local buffer destined for a given remote node and ships the buffer once it is full. This aggregation is done at the node level, so these buffers are actually shared across the node, giving us even better aggregation. This slide shows the API for the aggregating stores data structure. I won't read through it, but it has methods to set the local buffer size, add an element, and force any partially full buffers to be communicated. Obviously, aggregation will delay the individual updates, but because this hash table is used in separate build and access phases, this is not a problem in the MetaHitmer application. Now, the third phase, after you've built this set of contigs, is to align the original reads against those contigs, allowing for imperfect matches. String matching is done with some variant of the Smith-Waterman algorithm, which is shown on the left. Perfect matches between characters are shown as diagonal paths, whereas insertions and deletions are horizontal and vertical paths respectively. In the worst case, it is an order n squared operation for strings of length n. In practice, we use GPUs for this computation as well as heuristics that reduce the algorithmic complexity by searching only for matches near the diagonal. We don't really care about poor matches in this alignment problem. Now, alignment here is a global problem in which we have two sets of strings, the original reads and the recently computed contigs. To further cut down on the cost of alignment, we will look for strings that are likely to match and only run the full alignment algorithm on those pairs. As illustrated on the right, this is done by hashing the k-mers in the contigs and then looking them up from the k-mers in the reads. Only if there's a match will the two be aligned. I'll just comment here that these alignment problems, both the pairwise and the many-to-many scenario, occur in many different genomics applications. And they're in fact used multiple times in MetaHitmer and other exobiome applications. As you can see on this graph, MetaHitmer scales well and up to 1K nodes. This is running a large environmental data set on the Summit system at ORNL using the GPU optimizations for k-mer analysis, alignment, and local assembly, which is separated here from the alignment phase. That local assembly problem is a very complicated set of GPU algorithms and are described in an SC21 paper to be presented by Muaz Awan. As I mentioned earlier, this paper is also being considered for a Best Paper Award. I'll also just comment that when we started this project, we were expecting to run the MetaHitmer code on CPU-based systems, and I've been surprised at how well the GPUs benefit this kind of problem with this counting data structure, hash tables, and graph algorithms. So just to summarize some of the features that are used in UP C++ in the MetaHitmer implementation, it uses certainly C++ templates just to make the code efficient. There's a lot of code reuse of things like hash tables and then distributed hash tables, which are built on distributed object types in UP C++. The asynchronous kind of logical all-to-all exchange where everybody is sending their k-mers out into buckets of a hash table or histogram that looks like an all-to-all exchange but is not done as a bulk collective call. It's done using these finer-grained, dynamically aggregated messages or data transfers. And this gives you much better scaling relative to the MPI implementation, as I mentioned, for the k-mer counting phase. There's a future chained workflow, so using the future features of UPC++ that allows you to then get multiple RPC messages overlapped, and they're sent by the node and then by the process so that we can get some aggregation also at the node level. So that helps also in terms of increasing our message size. And we use the promise and kind of fulfill feature of UPC++ that allows us to trade off the memory use, which with the performance, and allows us to live within a fixed size memory footprint, which is very important for the UPC++ for this MetaHitmer application, which tends to be very memory intensive. And so those are all some of the features of UPC++ that are really valuable in the MetaHitmer application. So just to wrap up, these are the resources that are available. I think you've seen these URLs before, but this gives you some ideas of where the UPC++ code and everything is available if you are just looking at this last part of the tutorial. There's also more training material available online, the formal specification of the language and the links to the publications and things like that are all available through those websites. Here's a couple of testament from the users of UPC++. Stephen Hoffmeyer, who wrote the latest version, MetaHitmer 2.0 in UPC++, really said it's been very helpful in producing these, using these features such as RPCs for rapid prototyping. And of course, he was also the author of the COVID simulation, the lung simulation example that I mentioned as well. And another user from PNNL talks about the value of this one-sided model, and once it's written in even another one-sided model such as SHMEM, MPI, RMA, or SHMEM, that it's very easy to adapt that code to UPC++. So hopefully that gives you some ideas of why you might want to look more at UPC++, especially if you have an application that has very irregular patterns of communication, of dependencies, of synchronization, things that will make it somewhat challenging to put it into a bulk synchronous style or make it inefficient in a bulk synchronous style. I think all of those are good sort of reasons to consider using one of these global address-based languages, and specifically UPC++, which gives you the convenience of these RPCs to really move computation around to data and helps actually with some of the synchronization issues as well as just the locality issues associated with that. So thank you very much. If you've made it all the way through our tutorial, we really appreciate you spending the time with us today virtually, and hope that you will have a great experience programming in UPC++. You also can contact the UPC++ group through that website as well, the URL I have here. So good luck, and thank you very much for listening.